Okay, so now why would we want to look at higher order derivatives? It is because of the connection with so-called Taylor polynomials, which tell us something about approximations for functions. And again, the material is in section 4.10 of the book. You can read it if you like. Well, let's recall the concept of a tangent line. This plays a role in this whole setup. So we have this function f of x. We look at a point A. F is differentiable in A, and we can compute the equation of the tangent line at point A of the graph of the function f, and the equation is equal to the following. So the tangent line at the point A is given by the function value at A plus the derivative of the function at the point A multiplied by x minus A. We have seen this thing more often. Now, for the moment we will not denote the tangent line by t, but since you see that it is a polynomial of degree 1, we will denote it by p1. And since this polynomial is created on basis of the point A, we will give an index A. So it is called P1 of A is the tangent line. And what are the properties, very important properties of this tangent line, this P1A, is that if you plug in the value at the point A, then we get x is equal to a minus a0, so we get the function value at the point A. And also if we compute the derivative of this first degree polynomial, well, then you see that this is just the derivative of the function at point A. So the derivative at A of the polynomial and the function are equal. Let us look at an example. For instance, if we take this base point A equal to 0 and the function is equal to sine of x. So if we look at the picture, then at the point A equal to 0 we have this function of the sine of x. We have this tangent line which is very close to the function when the point that you look at is close to 0. And for instance, if we look at the point 0, 1, then we will compare the function value with the value of the polynomial, the corresponding first degree polynomial. Now, what is the equation of the tangent line at the, if we look at the base point A equals 0, it's equal to the function value at 0 plus, well, the first derivative at 0 of the function multiplied by x minus 0. So this is just the equation of the green tangent line. Now, if we plug in the value 0 at sine of the function f of x equal to sine of x, we get sine of 0 is equal to 0. The first derivative of sine of x is cosine of x. So the first derivative at the point 0 is equal to cosine of 0 is 1, multiplied by x minus 0 is equal to x. Now let us try what happens if we compare the sine of x, sine function at the point 100th and this equation of the tangent line at the point 100th. So we get sine of 0.01 is approximately equal, if we just plug it in some computer program, to 0.00999983. And if we compare it to the polynomial evaluated at the same point, then we get here 0.01, so 1/100th. And you see that the difference is already very small. So the tangent line is in fact a good approximation of the function value, provided we are very close to our base point. Now this difference is smaller than 2 times 10 to the power minus 6. So, however, if we look at the function value at the point 1, sine of 1, then this is approximately equal to 0,84147. Well, okay, I will write it. And if you evaluate this first degree polynomial at the same point, we have to plug in the value x is equal to 1, and then the difference between the function and the first order polynomial is of the order, say, it's less than 0.15, is of the order 15%. So if we are farther away from the origin, from our base point a equals 0, then this difference between the first degree polynomial, this tangent line evaluated at the point, and the function value at that point is already quite large. So it's of the order 15%. So this is a bad approximation. Now what we would like to do is somehow bend this tangent line a little bit, so that it will approximate the original function a little bit better. Why would we want to do that? Well, clearly, as you can see from these formulas, it's very hard to determine the exact value of sinus of 1. And if you plug in sine of 1 at your calculator, you do get an answer. And the question is how to get this answer is clearly by doing approximations, by calculating approximations in some clever way. And this is exactly what we are going to do. So the task is to bend the tangent line in a way that we can better approximate the value of the sine at point 1. And this means that we will, well, the idea is to use a second derivative. And what conditions should we satisfy? This means that we want to have a second order or a second degree polynomial, which we denote by P2a, because the base point is a, such that, well, the value at a of the function and the polynomial are the same. The first derivative should be the same, but now also the second derivative should be the same. Now, what would be the formula of such a second order polynomial? It means that our second order polynomial should look like this. It is equal to the function value at a plus, so it's just the first part of this function is the same as our first order polynomial, which we put here, plus third term, which is the second derivative at a of our original function, multiplied by the difference of x and a squared divided by 2. And if we now take derivatives, second derivatives, then we get, and plug in the value a, then we get precisely the second derivative of our function at the point a.